Hello, welcome back to another episode of the Oxford Online Maths Club. My name's James, and today I'm joined again by Leo.
Hello.
Leo, you were on the Maths Club a couple of months ago. We did some stuff about prime numbers together. I
Yeah,
think? Yes, that's what we did on the
yeah,
live stream
we
last
did
time.
10 times, I think.
Yes, Maths and Primes. This time we've got you back to talk about maths that you actually work on because you're a default student, right?
That's right. So I'm a first year DPhil student here at Oxford, and my maths is population genetics. So we consider different models in biology, many different models in biology, and see if we can tell stuff about real life using those models in biology.
Bro, so if there's fans of biology in chat, or if people watching live, I guess, have questions about mathematical biology, we're going to try and do some of that today. It's quite fun last
Mhm.
time doing something completely different to the prime numbers we were talking about before. Hi to people in chat. I can see A, Herb, and Andre and Shrift in chat. I'm going to run a little poll to find out how their day was. Always interested to know how people's day has been. Herb asks what for our favourite animals. Leo, have you got a favourite animal?
Um, I do, and it's quite a narcissistic one. My favorite animal is the lion.
I thought you'd pick lion.
Yeah,
You're right.
yeah, but also because of its extreme laziness. Most
Right,
of the day
okay.
it's been sleeping.
I put lots of
That's pretty cool.
I put lots of predator animals in the thumbnail for this, just in case any predators appear during this mathematical biology live stream. And it's good to know we've already ticked the lion box.
Mhm.
That's fantastic. Uh, Chat is currently having a 4.1 star day, which is alright. I don't know, am I having a 3 or 4 star day? Yeah, Aya has spotted the Leo Lion link. Oh, that's fun to say. Quick adverts while people are doing the poll for how their day is. Um, Look at all this junk I've got on screen. We've got. Oh, the banging noise is very annoying. You might remember we had Eve on the stream last week. Eve showed us some mathematics, but also a poster advertising a step summer school. It had that photo with Eve with her feet on the desk. That's been kind of updated to this poster on the right with details about the step summer school. If you're interested, you could search for Murray Edwards Step Summer School if you want to find out about that. Oxford's running open days. We're supported by the Maths Institute and by Jane Street. Jane Street have got some puzzles. I was looking at this puzzle they've got with Jenga blocks and stuff on their puzzles archive. They've been doing this for quite a while, so there's quite a lot of puzzles in the archive as well. One involving Jenga blocks and oh, it's like those puzzle hunts. The actual puzzle is hidden within the puzzle. Anyway, a rabbit hole there. And if you want another rabbit hole to go down of exploring things, I've got some updates to the further reading. So Eve's extension notes that Eve mentioned last week are coming soon. I need to type them up, and I haven't typed them up. Sorry, everyone. But update Maria from 2 weeks ago, who was on to talk about music. Maria suggested that she could make a playlist of YouTube recommendations. That now exists. That has been made and that's been added into the further reading. So if you're one of those people who reads the further reading every Saturday or something, then if you you won't have Eve's one yet, but if you go back to Maria's one and read it again, there's more links and YouTube stuff in that one. We've made it complicated for you. That's what we're like. At some point, I'll type up Eve's notes and then, goodness knows, we'll see two for the price of one at some point. Okay. Hi, Ria and Zoe and Neutrino and Aya in chat as well. Averages dips down from 4.1 to 4.0 while I wasn't looking, so I'm going to close the poll before it goes any lower.
Oh,
There we go. Neutrino's excited for the playlist. So yeah, it's worth doing all of the squares on the screen with the different things. One person is now going to go and see Maria's playlist. Okay. Ooh, that's a lot of screen tearing. Okay, I'm going to hand over to Leo, I think. Partly because
mm.
you're the mathematical biology person, and partly because there's loads of banging noises coming from a building site next to me. Um, Over to you, Leo. What are we doing today?
So today I was thinking we could look at different population models that people have considered. throughout time and what they're supposed to represent. And also what the process is of turning that piece of biology into a piece of mathematics and what you can say about the biological system based on that. Just like the whole process of the interaction between maths and biology, really.
Okay, let's have an example of some population modelling.
Okay, so I think it's useful before going on to more complex examples to start with something simple that maybe the audience will be more familiar with. So I um I would guess quite a few of you would be familiar with maybe the Fibonacci numbers at school. And so this is one of the oldest ones considered. I think the history behind it was Fibonacci was considering the population of bunnies throughout the years. And actually there is a simpler model than even that, but we're not gonna consider that here. So bunnies go through 3 phases. And let me draw. Oh, actually, James is drawing bunnies. So you have small bunnies, then you have big bunnies, and big bunnies give birth to small bunnies.
Are those your bunnies? Hang on,
Yeah.
let me help you out here.
Okay, thank
You
you.
can't just do stick figures. This is an artistic
Yeah,
stream.
it's yeah, it's
Sorry, carry on.
so big bunnies give birth to small bunnies once per month. They're they reproduce very fast, and small bunnies turn into big bunnies once per month. And this is the growth phase. This is the growth phase. And also in this model, bunnies never die, which is an interesting assumption, but it makes for a simple model, so it it fits the job quite well. So if we were to model this mathematically, we could look at the number of bunnies after, say, n months, and we start with one bunny. And that bunny is a child. So what happens? Next month, that bunny becomes an adult. Then the next month, that bunny reproduces and produces a child. So there's 2 bunnies.
The adult and the child.
The adult and the child, important.
You could say that 1+1 is 2. Welcome to the Oxford Online Maths Club.
Yeah. Very important fact of mathematics, of course. And then you have one adult and one child. So now the child grows up, and then the adult gives birth to another bunny. And so we have 3 bunnies, 2 of which are adults, 2 of which are adults, and 1 of which is a child. The 2 adults reproduce to give 5 bunnies, the next generation. And then
Right, this is the weirdness of the model, isn't it? That 2 adult bunnies means you get 2 children, 1 each.
Yeah, that's yeah.
I think sometimes people say this is a bit like strawberries in a way, but they sort of spore off. An individual can spore off an additional plant. But never mind. Okay, yes. You've got to 5 bunnies.
I think this model makes more sense with, maybe strawberries or bacteria.
I can't draw strawberries, so it's going to have to be bunnies.
Okay, it's going to have to be bunnies. But by the time you have 5 bunnies, 3 of them are now adults, because the one that was previously a child has grown up, and then 2 of them are children. And so we see that at a certain generation, if you look at the number previously, this tells you the number of adults. And all these adults reproduce. So then the number of bunnies the next month is the sum of the 2 numbers beforehand, if that makes sense. Or I don't know
Yeah.
if I could explain that the best, but if
So
here we start, sorry,
you'd think it'd be the sum of like all of them or something because the bunnies are immortal, but in fact, the previous one already included lots of grown-up adults who have been around a while. So to avoid overcounting them, you can
yeah,
just add on. Yeah, I'm overthinking it, but yeah, you add up the previous two
yeah,
numbers according to
yeah.
this.
So if we add a bit of notation and we call xn the number of bunnies after n months,
Hmm.
then we see that xn minus 1, the number of bunnies the month before that, is also the number of adults after n months.
Right. They all grow up, so now you have that many adults.
So there's that many adults. And to get the number of bunnies in the next generation, all the adults we produce.
Right.
So all the adults create another bunny. And so if you add that to the number of bunnies that there currently are, because none of them die, then you get the number of bunnies in the next generation.
Smashing.
Yeah,
Okay, and that's the famous rule behind the Fibonacci numbers, that they're a
yeah,
sequence where you add up the previous two terms. Here
yeah.
in
This is the
enacted.
thing.
Yeah. Shrist, it's not just you. Everything is really laggy on everything. I'm going to try and kill some processes to make my computer happier.
Okay.
See what I can do. See if that makes things better. Ooh. Sorry, I've interrupted. But I wanted to show you quickly, while you're keeping track of the adults and children, someone showed me a really good way of doing that using vectors. So what you can do
Okay.
is you keep track of like the adults. Oh, I hope I get this right. And the children.
Okay.
So this starts as no adults and one child,
Yeah.
and then later on that child grows up to be an adult, and you get, oh gosh, what do you get? No children, because nothing's been born yet. But
Yeah.
the next one, the child grows up, so you now have, well, you still have one adult, but the adult gives birth to a child.
Yeah.
And there's some sort of crissy-crossy thing going on where you keep track of the adults spawning some children who will very quickly grow up. So we get one child, and this being the sum of what you had before, all the adults before.
Yeah.
So it'd be like adding, and that goes down here. And there's a way, if you're good at vectors and matrices, there's a way to make this into a vectors and matrices problem, which I quite like, because I think some people in A-level are just getting to grips or just learning some sort of vectors and matrices stuff for the first time. So seeing something familiar in a weird context, new context.
Yeah. And I think you could probably quite nicely do this with vectors and matrices. If you do just call an the number of adults, and cn the number of children in generation n,
Right,
and
then you've got two sequences.
then the number of adults in the next generation is the number of adults plus the children who have now grown up, right?
Right.
And the children in the next generation is just the number of adults in the last generation, because they each give birth to a child. And so now the interesting challenge is to write this in matrix form and to see if there's a matrix that can represent this transformation for people who are familiar with matrices.
Okay, to actually find the matrix transformation.
Yeah.
Might leave that as homework for the people who... Can we leave that as homework for the people who
Yeah.
know matrices?
Yeah,
Also-
I think that's a good idea.
Okay. Also, can chat let us know if the video gets better or worse? That'd be nice to know. We're quite laggy at the moment because my poor little computer is trying to do too much stuff at once. Just can't keep up with all these rabbits. I think the audio's okay.
They reproduce
Touch
too
wood
fast.
at the moment. Yeah, too fast. Yeah. Okay. Good. So Fibonacci numbers. I like them. They're keeping track of the population and keeping track of a kind of a fact about the population as well, rather than just sort of a sheer number of rabbits. There's a distribution of whether they're adults or children. It's kind of different statuses that rabbits might have. The kind of status of being a child or the status of being an adult.
Mm-hmm.
Yeah. Okay. I don't know if chat have got any ideas about how to make this model more realistic. I suppose Leo as well. If you've got any ideas about how to make this more
Well,
realistic.
well, one thing for sure that you would like is to incorporate the fact that those rabbits, or most biological systems, at some point die, and I think that's kind of like inbuilt because we have finite resources. So the problem here is we have exponential growth, right?
Yeah, it does. That's a fact I know about the Fibonacci numbers, that you end up with exponential growth.
Yeah. An interesting question for chat is, can you prove that there's exponential growth? Do we get some sort of formula for the number of children? But yeah, one thing we see is exponential growth, and that doesn't feel very realistic on our planet Earth because there's finite resources,
Yeah,
right?
people were talking in chat about the Earth being run over by immortal rabbits, like if the rabbits never die. Um,
Yeah.
there's a suggestion to add in death. Actually, multiple people have put, yeah, the rabbits must
Mhm.
die in chat. Not quite that word for word, but the rabbits must die.
Yeah, I think
And
that's true.
uh, the user with the username A, who maybe knows, maybe has seen things like this before, suggests that we add in some foxes, because foxes eat rabbits as a way for them
Ooh.
to die. I think they're trying to bridge for us a beautiful segue towards some sort of Volterra model, which is something to do
Yeah,
with, yeah, rabbits and foxes. I think I've seen something
I
like this
would.
before.
I
Do we
have
want to say
seen.
anything about that, or I can't remember if that's
I
on our
think it's an
plan?
interesting. Yeah, I think it's an interesting model because the dynamics of it are a bit different. But it has the advantage of having population control, and so it adds a level of realism. It also has the advantage of incorporating the fact that you have predators and prey.
Yeah, and you can get interesting dynamics, right? You've mentioned that you can get, if you have competing populations, or in the predator prey case, a population that's
Hmm.
predating on the other one, you can get interesting balance behavior, I think, and
Yeah,
an interesting sort of cycling
yeah.
behavior where there's kind of
You
peaks and
can have
troughs.
cycling behavior. I
Hmm.
think. Do we want to introduce that model nicely?
Yeah, you have a go at
Oh,
doing that? I'm going to think about some chat saying about whether we can make the vectors 3D to make
okay.
to account for death, and I'm not sure. Oh, it's like is the third entry in your vector there something depressing like deceased rabbits? Oh, this is making me feel sad now. Right, let
So,
you set up
so I'm going to
log to
write
Volterra.
Rn to be the number of rabbits in the nth generation, in nth gen, and Fn to be the number of foxes in nth generation. And the way this model is going to work is um, you have some rabbits, which I'm going to draw as people because I'm more comfortable drawing people, but they're smiling because I imagine rabbits are smiling. And there's an infinite plane of grass. So the rabbits eat the grass, and the grass is infinite, it regenerates automatically, and they're happy to eat the grass. And so without any predators, the rabbits eat the grass and reproduce. And they reproduce exponentially, similar to the Fibonacci numbers we considered above, except in this model, unlike Fibonacci, we don't consider adults and children. So we only consider that there's rabbits. They don't have ages. So then in this case, the rabbits would reproduce like 1 plus alpha or to the n, so exponential growth. However, you also have foxes. you also have foxes. And these foxes, they eat rabbits. They do not feed on the grass. And since they completely rely on the rabbits, they their reproduction, no, sorry, not their reproduction, their population growth would die in the absence of no rabbits. So then we have a factor of minus, let's say 2 f of n. Oh, and sorry, I should say this I'm emphasizing just because afterwards we're going to get a differential equation out of it. So this means that they would just die in the absence of any rabbits. But when they eat rabbits, they're happy. And so here you have a factor of Fn Rn, which means that proportional to the number of foxes and proportional to the number of rabbits, this is how much they eat. Fn Rn is the amount of rabbits they eat.
I like the way your foxes look even happier than the rabbit people. If you've just joined us, we're making Fibonacci. We're making the Fibonacci thing about rabbits into a problem with rabbits and foxes. We've got two equations. The first one, I'm going to read it back just to check I've understood. The number of rabbits in the next generation, n plus 1, is, so they say 1 plus 2 times Rn. Okay, so it's sort of
However,
some amount, the rabbits you had before, plus they've had some kids.
so yeah. However, they also suffer because when the foxes eat the rabbits, the foxes are able to reproduce because they've eaten, and this gives them energy to reproduce. But the rabbits, well, they've lost a rabbit.
Right, okay. So you've got this term on here with a minus sign here because we're losing some rabbits, and a plus sign here because we're gaining some sort of foxes.
Yeah.
Sort of the conversion mechanism here for converting a rabbit into a fox is gruesome and not worth thinking about. But the fox population does well out of this interaction.
Yeah.
And the bit that I like is that this is you've done this term as the product of the number of foxes times the number of rabbits.
Yeah.
Which is larger if there are more foxes, and it's larger if there are more rabbits. And that's kind of because I guess the interactions between foxes and rabbits are more likely if there's more of either of them.
Yeah, it's proportional.
Right. Okay. Some sorts of chemistry are like this, I think. Trying to
think
chemistry reactions at one point.
I think in a reasonable model, you'd have a factor in front of here and in front of here, which would make this a lot.
Yeah, there's a bunch of numbers, aren't there? So I'm going to circle them quickly. But this kind of rate at which foxes die is a number you could change. This rate at which rabbits are born, in addition to the rabbits you already had, is a number you could change. There could be a number in here for how effective the foxes are at eating rabbits, and there could be a number inside there for how good that is for the fox population.
Yeah.
Ugh. So many numbers. Okay, so this is a rather complicated system. I can't see what we're going to do with it.
Yeah, well, the idea here, and this is also similar ideas to what I'm doing in my research as well, is to go from a discrete system to a continuous system. And the Lotka-Volterra equations are mostly seen in differential equations. But there's a nice way that you can go from these discrete equations to the differential equations, and then it becomes almost easier to analyze.
Okay, so I reckon people in school or A-level or equivalent are just about seeing some differential equations. In fact, I think you learn differential equations before you learn about difference equations or complicated sequences and series, maybe, depending on what order you learn stuff, I suppose. But you're telling me that there's a differential equation version of these equations that we could look at?
Yeah. Yeah, there is. And so the idea behind that is to look at the number of rabbits, but look at the difference of the number of rabbits. And that is what's really important, because this tells you whether it's going up or down and by how much. And here you get 2 times the number of rabbits minus the number of foxes times the number of rabbits. And then instead of instead of incrementing by units of 1 in the future, you can increment by smaller units in the future. So you could look, for example, units of 1/2 in the future.
So instead of looking 1 year in the future, I might be looking 6 months in the future. Or
yeah, instead of 1 year in the future.
It's just the way you go from the kind of discrete, I have R1, R2, R3, R4, and you try and fill in the gaps to say what would R1/2, R1/4 be, to get to this kind of continuous picture of what the population is.
And here you would get 1/2 times this difference, assuming that it's roughly linear. Assuming that the transition from n to n plus 1/2 and n plus 1/2 is n plus 1 is roughly linear, you just multiply by 1/2, because you increment by 1/2 of it in the first time and 1/2 in the second time.
Okay, so there's a rate of change here that turns it from, if people have seen differentiation from first principles, they'll have seen the idea that if you have a curve, then you're looking at the difference between values on the points, and if you move those very close together, you get something like the tangent or the derivative. Okay, is this going to turn into a beautiful differential equation for us?
Well, the magic is to put the 1/2 on the other side, or the next step is to put the 1/2 to the other side, and then realize that this reasoning works not just with 1/2, but it works with any small positive number.
Okay, so then the left-hand side looks like a derivative. It looks like the first principles, the change, the tangent, the gradient of the tangent at that point. So the derivative, the rate of change of rabbits.
Yeah.
It's a bit weird to think about the continuous limit of how right now the number of rabbits is changing by some amount, because a year from now it will be different, so it's been changing all the time in some sort of continuous limit.
It's been changing all the time, but by very, very small amounts, because here you multiply by 1/2 because the unit of time is smaller, but if you replace that with a quarter or an eighth, it changes by very small amounts.
Part of this is the kind of imagining that we can have fractional rabbits as well. I think that rather than the rabbit population going from 1 to 2 to later 5, like in the Fibonacci numbers. 1 to 2 to 3 to 5, like in the Fibonacci numbers, then that you could have a system, and it's a mathematical model. To have a fractional, not integer number of rabbits.
What's important is the fraction of rabbits compared to the fraction of foxes.
Yeah, maybe we're imagining that 0.1 on this actually means 0.1 brackets million rabbits or something. So maybe we can interpret it like that, and maybe it's the ratios that really matter, because
it's the ratios that really matter. And also this model is idealistic in the sense that if you wanted to really count rabbits or count foxes, you would get discrete numbers, but you would also have discrete time. You would only look at rabbits, maybe every 3 days or every few weeks.
I guess
you to bring it to.
Well, no, I was going to bring it towards statistics, because I think people have seen this discrete versus continuous split in any statistics that they've seen, where they might have seen some maybe probability events or something, where the events either come from a discrete set, like you roll a die and you get a number from 1 to 6, or they come from some sort of continuous random variable. So you select a number between 0 and 1 at random, or you have some sort of binomial distribution that gives you a real number as the output. And this kind of distinction between when is the discrete thing, a bit like the continuous thing, comes up lots of times
Yeah.
in statistics and kind of continuum modeling.
Yeah, continuous stuff is the limits of discrete stuff, and that's why it's so powerful. And this theme is going to reappear later on. And I don't know, in my opinion, the continuous stuff doesn't really exist, but it's very useful. So this is why we're still studying continuous stuff.
Right, hang on, which way around? The continuous stuff doesn't. Is that what you
Uh,
just said? Yeah, okay, that way
yeah,
around where the ones with fractional rabbits
yeah, the
doesn't.
fractional rabbits don't exist, but they're a very useful modeling tool, and it's easier to get results about the differential equation than this to get results about the recurrence relation.
Right, okay. So if this thing on the left is a derivative, if it's
Yeah,
the change in r over t over time, perhaps,
yeah,
then I've got some stuff on the right hand side, and I could do something similar for the foxes as well. I guess I'm going
yeah,
to get a -3 because you're going to subtract.
yeah.
Okay. So you build some
So,
differential equations.
so if you believe that this happens for smaller and smaller units of time and that having the continuous time is useful, then you would get this differential equation, where the first term in the differential equation is the exponential growth of rabbits. And the second term in the differential equation is the rabbits being eaten by foxes, and that depends on the number of rabbits and on the number of foxes. And it's a product of those two, because foxes and rabbits interact 1-to-1 in
Got it.
this model.
Yeah, and you said exponential because if the FRN term here wasn't there, if there wasn't
Mhm.
this being eaten by foxes predation, then this is the classic differential equation for a function whose derivative is multiple of itself. That's the exponential function with like e to the
Yes,
2t or whatever.
yes, exactly.
Okay, I saw someone in chat suggest a differential equation a moment ago for exponential growth, and hey, look, there it is out of the
Yeah,
limit.
if the number of foxes is 0 at the beginning, it will actually stay 0. So then this differential equation would work.
Right, and this one's got that -3 I predicted because you're
Yeah,
behind the scenes. You've done this subtract fn to work out the
yeah,
change.
yeah. I have.
Okay, uh, and I think the modelling of these different differential equations with
Mhm.
continuous time, I suppose, the modelling of these is a bit easier, maybe, or I'm trying to read out a comment from Shrist.
Um,
Sorry. So why do we do? Why have we
well,
done this? Is this like a modelling thing? Or?
um, so first of all, this gets rid of the unit of time. So now we could look at rabbits in every 3-week generations or every second, or look at rabbits every second, or we can choose any unit of time that we would like, which is nice. But also, I think another thing is just that differential equations are a bit easier to solve, or at least this one is, because for this differential equation, what we can do, for example, is solve it and then graph the number of rabbits compared to the number of foxes. And an interesting pattern emerges. And the pattern that emerges, if you can allow a bad graph, is you can see the number of rabbits increasing and then decreasing and increasing and decreasing and just kind of oscillating. And what follows is that the number of foxes, while the rabbits are increasing, it follows a sort of like delayed increase. But then as the rabbits' numbers increase, they start increasing as well, and they start increasing as well. And then they reach their tip after the number of rabbits has been decreasing for quite a bit, and there's a lot of them. And at this point, for example, there's not many foxes and there aren't too many rabbits. So the number of rabbits continues increasing, But as the number of foxes increases, at some threshold, the number of rabbits have to stop increasing. But then when the number of rabbits decreases too much, and so does the number of foxes, and then they start decreasing. And so what you essentially see is kind of like two curves that are oscillating, but they're out of sync in a way, if that makes sense. And this behavior can be deduced from the differential equations themselves.
So there's some analysis tools that you can use on differential
Yeah,
equations, and I know that you can, if you want graphs like this, you can give them to your computer, and your computer essentially tries to work out how to get from a start time to an end time by following this rule about how the thing should change. And I think something to link it together is that your computer is kind of approximating it because it has to, it's a computer. It
yeah,
can't do continuous time really, but your computer maybe has control over what size steps it takes,
yeah.
which is an
That's
advantage. Yeah, okay, advantage over the discrete model where you'd be stuck taking the discrete step sizes. That if you feed a
yeah.
continuous time model to a computer, it's got a bit more control to say, well, I'll take little steps here to resolve this detail, and then I've checked I can go back to doing larger
Yeah,
steps.
that's actually a really good point as well. That when the computer simulates any differential equation or most systems in mathematics, it has no choice but to go in the discrete world because the computer can only do a finite number of operations.
Yeah, it's weird, isn't it? We take these discrete problems, make them
Mm.
continuous, and then pass them sometimes to computers to approximate back into discrete
Yeah,
model. Where the discretization there is trying to do something very complicated, but it's trying to model the kind of infinite limit of
exactly.
what was going on. So as if there's no effect of step size.
Yeah.
Somebody's asked if I can
Uh,
sub the equations into each other, and there's actually kind of about four unknowns. Well, there's a lot
four
going on
unknowns.
here
There's
because
two unknowns, the number of rabbits and the number of foxes. Or are
that's
there more?
true. I guess I'm also considering the derivatives of those things, but I'm being silly, aren't I? I could plug it back in by
Yeah.
differentiating.
Yeah.
So I could, what could I do? I'm sure it would
So
be nice if I could just stick them together or something.
mhm. If you have the number of foxes and the number of rabbits, then you know all the information about the system because you also
True.
know their derivatives.
Yeah, okay. If I know both of them, I'm just thinking I can't take. Would be nice, but I can't take this f on the left over here and sort of magically plug it in here to be done or something because this is the derivative and that's the function.
Oh,
No,
to
but
relate the
I don't know.
differences
I'm
with the
imagining if these were just simultaneous equations for two variables, then I'd be good.
oh,
But it's kind of two differential equations for two
hmm
two functions. It's a bit harder.
yeah.
I can't remember for
So
logic Volterra. Is there something clever you can do to plug one into the other?
um I don't think so. I think what you usually do is you calculate the stable points. So the points where the derivatives are zero. So this is like analyzing a function by looking at when the derivatives are zero. So you solve this system of equations. So it's like if you have a function and you want to find the minimum, or if you have a system of one ODE and you want to find where it's zero. And then once you look at those stable points, you look at the behavior around those stable points.
Yeah.
And the idea behind that is when it's close to those points, is it going further away? Is it going away from those points? Or is it going towards those points? Are they attracting? Or is it doing some complicated behavior where it comes towards those points from one angle, but then leaves from another angle?
There's a lot you can fit into two-dimensional space. It's
And
good.
yeah,
Um,
so one possibility is you have going away from the point where the point is unstable, and no matter how close you get, it will leave. One possibility is it spirals around. One possibility is it will kind of come close from one axis, and then leave by another axis. And
Sort of different behaviours, and those
yeah,
pictures are taking place. Those pictures take place in rabbit fox space, I think, where
yeah,
you're ignoring time and thinking about how on a map where the axes are. I've seen one of these before. The axes where the axes are rabbits and
yes,
foxes. So you don't visualize time; you just visualize the relative, or visualize the populations.
yeah, that's it.
Which reminds me, so you can't differentiate one and plug it into the other because they're non-linear. They've got this
Yeah,
kind of
that's
multiplication relationship. Something
yeah.
you can do is to think about this derivative. I think I've seen something with this, where you think about the derivative of the number of foxes with respect to the number of rabbits, which is really not worth thinking about too much what that means. But that's surprisingly not too bad. I mean, you can write it in terms of Rn and Fn
Yeah,
to get something like this. And so this loses track of, it's the ratio of these things, I think. So this loses track of when things happen because I've kind of cancelled out time. But it's something to do with, in this space of rabbit fox space, it's something to do with the gradient on the curves in that space, not the gradient here against time, but the gradient over here in this space. I think maybe using some partial fractions or just rearranging stuff a lot, I reckon you can maybe solve that into some implicit equation. Chat
I
will let me know. Get all the f's on the left, separate it. Separation of variables. We're not gonna do it now, but
oh yeah, separation of variables would
I
work.
reckon
Yeah.
that's amenable to separation of variables, a trick that some people in chat might know. Of course, we've lost track entirely of when stuff happens. We're going to get down to some sort of horrible equation for f of n and r of n that we won't be able to solve. This has got some weird like logarithms in it or something, but we might have to plot some curves. Anyway, never mind. I quite like this kind of abstract fox space up here for where the rabbits and foxes live.
Yeah, it's a funny space because it doesn't feel like it really means anything, but it somehow gives us the way of thinking where we can use mathematical tools.
And Trist asked whether the intersection points where the number of rabbits and the number of foxes are equal, it might feel relevant because the populations match at that point, but it's not one of these. It's not one of these stationary points because at that moment the foxes are eating. The foxes are eating really well. Their numbers are increasing. This is
Yeah,
terrible news for the rabbits. They're on the way down.
yeah. And
Yeah.
also, if you had a more realistic graph, I think the number it would be possible to have the number of foxes never intersect the number of rabbits. I
Right.
think
You
it
could.
would be entirely possible to have like small bumps like this.
Oh, I see. They don't have to intersect because you might just have loads and loads of rabbits. You do tend to have more rabbits than foxes around the place, I think.
Yeah, yeah, you tend to have yeah, with predators need to eat a lot more prey
Okay.
to sustain themselves.
Okay, we've got some homework for chat to maybe try and do something like this, using something like that, to analyse these equations. And who knows, maybe we'll get some graphs out as well if anybody gives this to a computer. We've got about 15 minutes on the clock. Do you want to switch to talking about the thing that you were telling me about before?
Okay, so what my work is mostly related to right now is a so both of those models that we had, first of all, there was Fibonacci, and Fibonacci is we're only recording one species, but we are recording two generations, child parent. And the second model, we consider two species now, but we don't distinguish parent child. So these are all modeling aspects of how we got the equations that we got and where they come from. But importantly, in both of those models, we do not record space. Animals, they don't live in space. I drew them as if they lived in space, but we didn't record the spatial locations of the animals. And that's an important aspect because it means that in essence, all the animals live in one dot and they can eat all the other animals and reproduce with all the other animals. And as we know about our world, we live in a space, a 2D space. And so, for example, a rabbit eating grass in the UK is not going to affect the state of a rabbit eating grass in Argentina, I would like to believe. These are relatively disconnected in the grand scheme of things. Whereas a rabbit eating grass in the UK is going to affect another rabbit eating grass 2 meters away from it. And so now we introduce a model. We can think of rabbits, we can think of any animals, but I think we should stick with rabbits just for consistency's sake. Where those rabbits, they move in space. And those rabbits live on a 2D plane. And there they are. Those are the rabbits. When they
That's your best rabbit yet.
Yeah. Thank you. And we have another rabbit here. And they do two things. First of all, they give birth to other rabbits, and the rabbits they give birth to will be somewhere close to them. Then they don't move too far away, so they can give birth to baby rabbits. And we also in this model we only consider rabbits. We don't consider any other species. So this is one species, but we consider the spatial location of the rabbit. So it's important that they give birth around them, like close to them. And they also die. So then this rabbit, for example, can at some point will die. Because this is another important thing about animals on this earth, they die.
Harsh
And
news for all of us, I'm sure.
harsh news.
Okay, so you got birth, but it's local, and death happens very locally. Okay, so I can sort of see that
So
if you set that up, then the rabbit populations will like grow nearby. The new ones will, I guess, do they grow up in this model? Do they get older? Or?
they don't grow up. They stay the same age.
Okay. So do the new ones ever spawn their own
Yes,
rabbits?
the
Oh,
new
okay.
ones turn automatically into adults. Like
Ah,
this model doesn't take into account age.
oh, I see. Okay, so they just get spawned as new
There are other
rabbits.
models similar to this one which account for age, where you have a certain period where you're dormant in a sense. Actually, it's mostly relevant for seed banks, for seeds, but you could imagine it as the rabbit growing up, in which case it can't move, it can't die, but it also can't reproduce. And then at the end of that, it turns into an adult and then it can do all of those things.
Okay, now I'm imagining a kind of oak tree or something that spreads acorns nearby, and eventually they'll grow into more
Yeah,
oak trees or something. Good. Okay, so we've got some spatial stuff going on.
yeah. And the novelty of this model compared to other models, is that this model, they give these rabbits, they give birth at a certain rate. So you can think of it as the speed of giving birth. So if a rabbit gives birth at speed 9, it means that every second, on average, it'll have 9 children. But no, wait, let's think of it more like in terms of years. Every year, it'll have 9 children on average. If it gives birth at speed 100, then it's a very productive rabbit with 100 children per year, roughly speaking.
Or a very happy oak tree.
Yeah.
Okay. So there's
So,
a number that you're tracking, kind of
yeah,
for each
and
rabbit.
this is a rate, and the rate is both for birth and for death. And the rate depends on the local population density of the rabbit. So in this scenario, you could draw concentric circles around the rabbit, and you could imagine that, say, a rabbit here would have, if this is our original rabbit in the center of those concentric circles, the rabbit here on the second, between the second and third ring of the concentric circle, will have much more of an impact on the rabbit than a rabbit here or another rabbit over there, completely far away, very far away.
So there's some calculation where other rabbits, based on their distance, influence this one,
Yes.
and they influence all of the kind of parameters, like how the birth rate and the death rate for that
Yeah.
particular rabbit. Okay. Which way round
This
is
rabbit,
it? So,
yeah, this rabbit senses distance. Whereas in our other models, no matter where you were, since we didn't record distance, the rabbits would act the same.
yeah, before we were treating them like a kind of chemical that was all mixed up with the foxes, and so that anything goes.
Yeah.
Okay, and is it the case that the presence of more rabbits, does that make them more likely to die or more likely to survive, or is it complicated?
So, essentially, in the parameters that have been chosen, it makes the presence of more rabbits makes them more likely to reproduce, but also more likely to die, and it makes them more likely to die faster. So essentially, these are parameters that we've chosen or that have been chosen in the paper, and the idea behind it is that if you have a lot of rabbits, they can help each other and cooperate, and so you are more likely to reproduce, because if there's no rabbits around you, it's quite hard to reproduce. But since there's such an intense, need for resources, they also die fairly quickly.
Okay.
But
So it's a complicated interplay between one rabbit on its own probably not going to have a great time, but too
Yeah.
many rabbits and it gets a bit overcrowded. Okay, so
yeah,
that's an interesting
exactly.
kind of trade-off which you can
Yeah.
track this. And I'm imagining that so far we've been describing this like it's a discrete model with 5 or 6 rabbits in, but I
Mhm.
think you mentioned that there's a continuous limit here as well, right? That you go to a kind of
Yeah, there is actually a continuous limit. However, this so the continuous limit says, let's start with let's see, wait, no, I'll write in black. It's easier. The continuous limit says, let's start with 10 rabbits and give them a weight of 0.1. And then we're gonna speed up time in a way that you can actually observe behavior. If you don't speed up time, essentially nothing happens. And then we look at 100 rabbits and give them a weight of 0.01, essentially so that the total weight is 1. Because when there's 100 rabbits, they're each a bit less important than if you start with 10 rabbits. And then you run the model for some time to see what happens. And then you continue like this, 1,000 rabbits with a very small weight. And then the same way that we were able to take limits, so to speak, in the differential equation setting, here you can take limits, and you can take limits to get the concentration of rabbits in a certain area. So now again, as we did for Lotka Volterra, you can't look at discrete rabbits. Discrete rabbits no longer make sense, but you have to look at the concentration of rabbits.
like the kind of like heat map of
Yeah,
I guess in terms of a heat map of rabbit density in different regions. I'm going
yes,
to try and draw that over here. I don't know. We've got a big park.
yeah. Yeah, that's exactly what I was thinking of,
I'm going to try
actually.
and draw the heat map. We've got 5 minutes on the clock, I think. Don't let me waste all of it drawing rabbit heat maps.
Mhm.
I don't know. I'm going to go red for lots of rabbits around here. Oh, that's not colouring in very nicely, and then a bit of yellow for not so many rabbits around here. And you can imagine that with a finite number of rabbits, that doesn't really make sense. But with a small enough rabbits and lots of them, then maybe some sort of density calculation makes sense.
Yeah,
And it's
that's yeah,
imagine
and that's
really technically
very-
difficult to get the interaction between these large number of small rabbits, to get the interactions correct and consistent when you're doing that, as you go to the limit of having lots and lots of rabbits. Is that something that's technically difficult to do?
to model the interactions between them.
Yeah, well, you've described quite a lot of interesting things about like the distance between rabbits. I could imagine that being really hard to think about if there's loads of them.
Yeah,
Okay.
yeah, it is. Yeah,
Um, in a way, you're converting some sums into integrals, I imagine, instead of adding across lots of individual rabbits. Are you doing a kind of integral across the?
yeah, you do. Yeah, you take the integral of all the rabbits, if that makes sense,
Right. Okay.
because you have
Like,
infinitely many of them, but each has z zero weight.
oh,
Except, yeah,
yeah, like how in A level there's a formula for center of mass that gets you to add things together, and then there's a separate one for a
into
continuous density, like the
exactly,
center of mass of a body, where you do some integration instead.
and that's exactly what you need.
Okay. Okay.
And
So what
there's,
happens? We've got a
there's one
complicated model
interesting,
of the relationships.
well, there's one interesting behavior that happens, which I think is worthwhile to discuss. And the behavior that happens is essentially you get a sort of clumping phenomenon. And we got this, well, this has been done not by me, but by others through computer simulations. By taking simulations of the model, you essentially get these kind of like groups of rabbits that just form together and that create, for people who know, like a sort of like lattice or like basically a grid with loads of different dots.
So just
And
the
the intuition behind the grid, can you see the grid?
yep, I can see you're doing
Uh,
patterns of rabbit colonies or something,
yeah.
or regions where the rabbit density is higher. What's the intuition here? Something to do with
So
the
if
interaction.
we circle this one, for example, this grid, then inside the rabbits inside, they feel the presence of the other rabbits inside of the grid as well, inside of that particular group as well. But they're far enough from the others. There's enough distance with the others that they don't really feel the presence of the others. But if now they have one of them has a child which moves outside of the grid and between two grids, for example, if they have a child here, then that child feels the presence of two grids quite strongly. So it feels almost twice the amount that others would, and so it would essentially die much faster. Because the higher the density, the more death is higher than birth. And so this prevents any rabbits being born between the grids. It's
Right.
a kind of regulation mechanism.
You'd expect, I suppose, so that the rabbits kind of repel each other because they're fighting for resources, and if there's too many there, they die out. But also
Yeah,
the rabbits are kind of attracted to each other because they reproduce more when there's more rabbits in an area. So you
yeah,
might imagine that all just kind of averages out into a kind of grey rabbit density where they're all a bit happy. But the answer is interesting. The answer is that they clump together to form
yeah,
localized regions where there's lots of rabbits getting on with it, and lots of regions where it's just inhospitable for rabbit life because they'd be competing with the regions. I guess there's some sort of interacting like
Yeah.
You can't quite draw the kind of resource map of which bits are their territories, but it's kind of interesting they form these little colonies. And I think somebody in chat was talking about the rabbits getting organised earlier, and
Getting organized
okay,
into groups.
I guess is each colony or each group inside each group is the birth rate kind of balanced out by the death rate? It's kind of stable.
Um, I would, yeah, I'd say roughly stable.
Maybe it depends on the actual numbers whether or not this is. Yeah, maybe it depends on the numbers, but
It does, but there is when there's low population, births are higher than deaths, and as you increase, you reach a sort of point where they're kind of equal.
right. So there's a colony and isolation kind of model that I don't know.
Hmm.
Maybe I should go and look for. Okay, and is anonymous in chat. This reminds them of Conway's Game of Life. I'll put a link in the further reading. Conway's Game of Life also has advantages and disadvantages of cells
Yeah,
being near each other.
yeah, it is definitely related. And yeah, Conway's Game of Life is another example of what we call an interacting particle system, where the presence of an individual is affected by the individuals around it. And I
Cool.
think it's a very cool area because you get all sorts of like strange organized behaviors out of very few simple rules.
What we're always looking for. Simple rules with unexpected consequences. Last question from me before we wrap up. We've been talking about rabbits all the way through. I just want to check: is this actually about rabbits, or is this about something else, like I don't know, human cells
Uh,
or biology, or
uh, I think the model is more related to fungus spores or pollen, I think.
okay,
So
other biological applications are available. It's um,
yeah.
okay. I don't want people to leave
No,
imagining that your office is entirely full of rabbits. And this
no,
is
definitely not.
this is the reason to be for being a mathematical biology. I suppose it's that thing about abstraction and working on the level where this could be relevant to lots of different things, especially if you understand especially if you understand simple rules with different parameters.
Hmm.
Maybe you come back and you do rabbits and wolves or something, and the wolves are a bit hungrier, so you just need to change a number in here. Or maybe you come back and you do a completely different
Yeah,
application that's got similar equations. Power of
yeah. And
mathematics.
these equations are also useful for chemical reactions. These Lotka-Volterra equations.
Yeah, yeah. Which is also good. Right, okay. I saw Zoe say that Zoe had solved this. So I think the homework might also be and sketch it, maybe numerically, maybe with computer stuff if need be, because the solution is pretty mad, assuming that what Zoe put in chat is correct. Okay. Anything at the end here as we're wrapping up, or anything you want to tell chat, or is it? Oh, just pause in case there's anything chat wants to ask you right at the end.
Oh, anything chat wants to ask?
I don't know.
Well,
We'll give them a second. I've closed the bit where I moderate chat or see what's coming up while people are typing. It's gone. My computer is so warm. We're doing our best. It knows it's 6 o'clock though, so it's calmed down a bit. Okay, we'll put together some further reading notes, I think, on things like Fibonacci numbers and Volterra outputs, and maybe something to do with research paper that you've been talking about as well. Otherwise, thank you very much for coming on the live stream, Leo. Thank you.
Thanks very much for inviting me, James.
Pleasure to have you on again. Thanks for people watching, and we will see you in 167 hours for another episode of the Oxford Online Maths Club. I have not got the button that turns this off. I closed the thing that stops the live stream was one of the things that wait, I can do this. We'll see you in 167 hours for another episode of the Oxford Online Maths Club. Bye.
Thank you, chat. Bye.